All right, everyone. Going to work through the analysis of a one-way ANOVA model, this time using Stata. The handout we're going to be working through is our Stata output, our one-way ANOVA model here. We had done the screening in the last video. Remember that what we're doing is we're looking at whether or not we have group differences in ratings of valence and arousal to an amusing film that we're wanting to use as an experimental stimuli, but wanting to see whether or not this is going to be a valid stimuli in a more diverse group of participants. So we've got people who we've categorized into white non-Hispanic, black non-Hispanic, and then a suboptimal other category, but then looking at differences across these groups. Okay, so we minimize this. We have our data that we just went through and finished screening. Again, recall that we have differences in our sample sizes, so ranging from 20 to 41. So differences there. Nothing too bad that came up in terms of distributions or outlying values or things along those lines. But the one thing that we didn't do is we didn't yet check for our homogeneity variance test. And so we'll do that now. If we go rope var, say valence by ethnicity. Okay, and again, we'll see our commands right here provided in our output. If we go through and we run that, this is going to give us our Levene's test for our ratings of valence. We get a number of different tests actually within the rovar command, but what we're going to look at here for our Levene's, this is going to be our Levene's test, and we see that in terms of ratings of emotional valence, we've got not evidence of reliable differences across these. So again, what we're concerned about with our Levene's test, recall, is a statistically significant Levene's test, which would suggest that the populations from which we're drawing our samples have different variances, which is a violation of our assumption. And so luckily, we haven't seen strong evidence of a violation of assumption here in terms of our ratings of emotional valence. But we can also take a look at we should also take a look at arousal. So if I go through, click my last command, and then type in arousal there, and take a look here. Now we do see that we have a statistically significant Levene's test. Okay, and this is a little bit concerning again because our sample sizes differ from 41 to 20, and so it looks like in terms of our ratings of emotional arousal, not only do we have an unbalanced design, but we also have evidence for likely differences in population variance across our white non-Hispanic, our black non-Hispanic, and our heterogeneous other group. And so in combination with an unbalanced design and evidence of violation of assumption, we're going to want to go through and make sure that we account for this in our analyses. Okay, so but let's start with valence, where we didn't find a violation of homogeneity variance. Our other screening looks to be pretty good. So what we can do here is we can just run a regular old one-way ANOVA. We've got an ANOVA command here, and so if we go through, let's go through and add these into a do file, so we're keeping track of what we're up to. Checking homogeneity variance there. Okay. All right. So what I'm going to do now is just run an ANOVA command. So I'm just going to set ANOVA ethnicity valence. Okay. Oops, got those switched around. Make sure that you don't do that, because it'll run it backwards. All right. And this is just going to run our ANOVA. Okay. Really easy here. So we've got our ANOVA. We see that we've got 99 people in our sample. Our R-squared value in this table, 0.0428. Keep that in mind. SPSS doesn't give you this, but Stata does. This is our R-squared value. If we're taking a statistic or a regression approach, this is also going to be our eta squared. Okay. If we look down into our ANOVA table, we have, so this is our overall model, and this is our individual effect. So ignore this line. That'll become important later, but not for this. So ignore the model and just look down. And so this is going to be our same sum of squares and mean squares breakdown that we walked through in class. So our sum of squares between, or our sum of squares effect here, or we talk about this as sum of squares treatment associated with our factor. So our sum of squares is going to be 7.72 or 71. Our residual, this is our sum of squares within, or our sum of squares error, 172.47, and then our sum of squares total. If we add these two together, we get this. Everything's summing up nicely here. Okay, our degrees of freedom for our between subjects effect, our sum of squares for our within, and then our sum of squares total. And then we have our mean squared. Okay. Remember that mean squared is just a term for variance. Mean squared is, all mean squared is just a variance estimate. If we take our sum of squares divided by our degrees of freedom, we get our mean squared, our variance estimate. Same thing with our mean squared error, or our sum of squares error divided by our degrees of freedom, we get our mean squared error, right? So this is our between subject variance, or the variance we're seeing across groups. Remember, in ANOVA, variance just means differences, right? This is how we quantify differences across our groups. If all our groups had the same mean, we would have no variance here. But our groups don't have identical means, and so we're seeing some variance across, and then we're seeing variance within. Recall that if group membership was the only thing that determined valence ratings here, then everybody in every group would all have the same score, right? But they don't. We know that people within each group differ in terms of their scores. That difference is error. Okay, that's something that we haven't modeled. Now, it might be systematic differences, it might be random differences, but if it's not accounted for in our model, it's error to us, right? So we have our variance that's attributable to our effect, our variance that's attributable to just random unaccounted error and differences. And so if we go through and we divide our mean squared between, or our mean squared effect, or our mean squared treatment, divided by our mean squared residual, or our mean squared error, or our mean squared within, this is going to give us our f-test and then our p-value here. So for these data, it looks as though we don't have sufficient evidence to claim reliable differences in ratings of emotional valence in response to this film across our different groups. It's not a huge p-value, but again, not anywhere near a place where we could call a marginal effect or things along those lines. So it looks like we're not seeing a whole lot, at least in these data, in terms of systematic differences or mean differences in ratings of emotional valence across our groups. Okay, but we still have arousal to take a look at, right? Now remember, though, that for our arousal measure, we violated our homogeneity variance, right? And so we need to do something different with that. And so what we can do is we can request a Welch test. Our Welch test is going to give us a test statistic that has standardized, an adjusted test with an adjusted degrees of freedom, and this is going to account for help us account for violations of homogeneity variance. So here it's just going to be W test, arousal by ethnicity. Now, one thing to note is that this Welch test, this is a user-specified program. So if you were to go to find it, and go W test and run that, what that's going to do is it's going to bring up this a window with packages. We're looking for W test. Okay, W test, here it is. And so if we click that, then you can go through, you can click to install it on your version so that you have it. If you try and just run W test without installing it first, it's not going to run. So this is something that you would need to run first. I've already got it downloaded here. So we go, if we go W test, make sure arousal and ethnicity. Okay. Arousal and ethnicity. If we run that, we see that we get just a small little output for our robust ANOVA, our Welch test here. Here we have our test statistic, our degrees of freedom, our numerator and our denominator degrees of freedom, and we find that we do have a statistically significant effect here. So basically what this is saying is that we would fail to reject the null hypotheses and conclude that we don't have sufficient evidence for reliable differences in ratings of emotional valence to this film across the population of individuals of white non-Hispanic, black non-Hispanic, and our other group. But in terms of differences in mean level of emotional arousal, looks like we do have sufficient evidence to reject the null hypotheses and claim support for systematic differences across those groups. Okay. Now, one thing we would want to take a look at and think about, though, remember that even though we have tests that help us correct for and adjust for violations of our tests, it doesn't mean we can ignore it, right? We still want to think about, so, you know, we ran these analyses to see if there are mean differences in valence and arousal across our groups. But it seems like, based on looking at our assumptions, that we have evidence for systematic differences in the variability, suggesting that the variance of arousal ratings differs across our groups. Okay, and so that might be relevant, right? If we're asking, you know, is this a good experimental prime to use in diverse samples? Depends on what we're talking about, right? Again, remember that if the only thing that determined ratings of arousal in this model, if we had a perfect model and group membership was the only thing that would determine arousal, then everybody who is in a group would all have the same ratings of emotional arousal, but they don't, right? And that variability is what we refer to this as error. And so it looks like we have more error variance among our in some groups versus others, and this is going to be something that we might want to think about and take into consideration as we're moving forward with this. Okay, so we have run our statistical test, but a couple of other things that we can do in Stata that's kind of nice is we can go through and we can request plots of our marginal means. Okay, marginal means in ANOVA or one-way ANOVA are the same thing as our observed means. We can do this in SPSS, but the nice thing that Stata will do is it'll give us confidence intervals around our output. And so this margins command and the margins plot, these are what are known as post-estimation commands. Okay, so what we do if we run a model, we've got a number of different post-estimation commands that we can run where it's just going to give us results from derived from the previous model. So if we want to start back with our, well, let's first copy so to keep our do file up to speed. So we can go through one ANOVA. Okay, but let's say we want to look at our marginal means for our valence. So we didn't get a statistically significant test, but let's say we want to go through and do that. So we're going to go through and rerun our ANOVA for valence. Okay, so this has gone through and it's run this, but then what we can do is we can run our post-estimation commands. So I can go through and I can say margins, go margins, ethnicity, and then we're going to put in no p-values, because otherwise this will just give us p-values on whether or not our mean values are reliably different than 0, which isn't super relevant to what we're doing here. So we'll go through, and this is just going to give us our means for each one of our groups, as well as confidence intervals around those means. And then what I can do is I can go margins plot, and this gives us a really nice graphical representation of differences in our mean values across groups. Okay, so again, in your handout, drop this down a little bit. You can see we're requesting our marginal means and our plots here, going through, and these two things together will go through and provide us a plot here. One thing to note is that your 95% confidence intervals that you've run here, this is going to be using your mean squared residual as your error term. Basically, this is just your pooled variance estimate for across all of your groups here. So note that that's the variance estimate that's going into the calculation of your confidence intervals here. Okay, so but we can also go through and let's say if we want to take a look at this for our, well, actually, I don't know, let's go through and so we go arousal. Now we know that we violated our homogeneity of variance assumption, but in order to get our post estimation plots and means, we'll just go through and run that model, and then we can once again hit margins, ethnicity, no p-values. This is now going to give us our marginal means of arousal and our 95% confidence intervals, as well as our margin plot. So here we're seeing sort of more of a difference here in terms of higher levels of emotional arousal in terms of our other condition relative to our other two. But that's something that we'll take a look at and follow up in terms of our follow-up tests for our overall ANOVA model. Okay, so last thing we can do in Stata is we can ask for effect sizes. Now recall that what we've got is we've got two different effects. We've got our eta squared and our omega squared. Eta squared, this is going to be a descriptive statistic telling us for these data the proportion of variability, of total variability in our outcome that's attributable to our grouping variable. Recall that we're taking this as our sum of squares treatment divided by our sum of squares total. So if we go back up to our ANOVA model, if we take our sum of squares treatment, or our sum of squares between our sum of squares effect divided by our sum of squares total, that's going to give us our eta squared value. All right, but remember that our eta squared value is going to be a positively biased estimator of the true population parameter, right? It's going to overestimate the population effect. And so what we can do is we can calculate an omega squared. Omega squared is still going to be positively biased, but it's going to be less positively biased than our eta squared. Okay, so if eta squared is interpreted as the proportion of variability in the outcome that's attributable to the grouping factor for these data, this is going to be the same interpretation, but except we're talking about within the population. So calculation of omega squared is going to be a little bit trickier. You're going to take your sum of squares between. You're going to, sum of squares between. You're going to subtract the number of groups minus 1. So this is going to be 3 minus 1. Multiply that by your mean squared error. Here in this case, it's going to be 2.843, right? And then divide that by the sum of your sum of squares total and your sum of squares error here. Okay. But the nice thing about Stata is that it will calculate these for you. So if I go through, and again, this is going to be a post-estimation command. So if I go back up and I run the model for, if I go through and I run the model for my my valence ANOVA, and then I type in estat, esize, is it ethnicity? No, just estat, esize. Okay. This has gone through and it's calculated my omega squared for me. And also calculated a 95% confidence interval around that. So omega squared for ethnicity is 0.043. So we would say, based on these data, about 4.3% of the variability in valence, rated valence scores is attributable to group membership. And the lower bound for this is going to be 0. Upper bound is going to be anywhere 13.2%, which is kind of big. Right, so this is going to be our eta squared, but we can also go estat, esize, omega, and this is going to give us our omega squared, right? And so again, remember that your eta squared is a positively biased estimator. Your omega squared is going to be always going to be smaller than your eta squared, and so if this is a population, a better population estimate, still a little bit biased, but we would expect that within the population for valence ratings among individuals, of the total variability that we would see in valence ratings to this film, that we would expect somewhere around 2.3% of the variability in those valence ratings to be attributable to our different racial ethnic populations here. Okay, so this is going to be a population estimate. This is going to be descriptive of what we've got going on in the sample, seeing the difference between these two. Okay, same thing, we can go back through and do the same thing for our arousal measure. I'll go back through, let's find it. So ANOVA arousal. Okay. So here we go. We've rerun our arousal model, and if we go estat, esize, and run that, here's our eta squared for arousal. It's going to be 5.8% of the variability in the variability of ratings being attributable to ethnicity, or racial ethnic groups, at least based on these data. If I do the same thing, I say omega, this gives me my omega squared. So for our descriptives for these statistics, our eta squared is 0.058, suggesting that about 5.8% of the variability in valence ratings in these data can be attributable to group level differences, with a lower estimate of 0, upper estimate of about 15.4% of the variability. In terms of our omega squared, we would say that we would expect across a population of white non-Hispanic, black non-Hispanic, and our unspecified other group, which is not optimal, but again, about 3.7% of the variability in valence ratings in response to this film being attributable to group membership at the population level. Okay, so again, go through here, modified this a little bit to remind you of your formula here. You can go through, calculate these by hand. We'll probably have you do that, but also this is going to be a nice way to go through and check your values on this. So that's that. Hopefully this is helpful. Let me know if you have any questions, and we'll pick things up in class on Wednesday.